The core of logic is a set of rules for obtaining new logical propositions from old ones. So let's go ahead and learn some of these rules. To start, let's make it a little easier to write logical operations. So we use variables like P, Q, or R to denote a logical proposition. So maybe P would be the proposition that I wore a red shirt on September 2nd, or Q would be the proposition that all humans are mammals. Definition. A logical operator is a rule for obtaining new propositions from one or more old ones. And these operators are defined by truth tables. Defined by truth tables. So let's do an example. We're going to jump right into an example of an operator that's defined by a truth table. So here's our first one. This is the negation operator. Negation is often written using this funny looking symbol. Looks like a sideways and backwards L. And it's also often pronounced not. So if we have a symbol like not P, we would just say not P, the negation of P. So what's a truth table? When we form a truth table, we figure out what the inputs of the operator are, and then we list out all the possible values of those inputs, and then we look at the outputs. So in the case of the negation operator, our input is just one logical expression. So just this little p here, that's our only input. So to form the truth table, we have one column per input. So here's my column for p. And I'm going to have one column for the output as well, not p. In the column for p, I'm going to put in all possible truth values that p could have. And since I have one proposition, and a logical proposition is either true or false, I only have two possibilities here. I can have a t, and I can have an f. Now, when I compute not p, well, the negation operator flips the truth values of the inputs. So when I have not p, if p was originally t in my first row, my not p is going to be f, and if p was originally f, not p is going to become t. So this is the complete truth table definition of the negation operator. If we sort of translate this into English, just to sort of get a sense for what the negation operator is doing, if P is the proposition that I hiked today, then not P is the proposition that I did not hike today. Let's go ahead and do some more complicated logical operators with their truth tables. The conjunction and disjunction logical operators are two binary operators. Binary logical operators have two arguments. They have two input propositions. And because these each have two input propositions, I now need to list out all possible combinations of truth values, and there are four possible combinations. So here I could have P be true and Q be true. I could have P be true and Q be false. P can be false and Q can be true, and both P and Q could be false. So these two logical operators are defined by these truth tables. So if as I'm writing these values in the last column of these truth tables, you're not sure where those are coming from, that's okay. These are the definitions, and if you need to, you can memorize them, although it's also possible to kind of get some intuitive sense for them, because the conjunction operator is sometimes called and disjunction is often called or. So let's go ahead and try. The conjunction operator is written with this funny caret here, so I've gone ahead and populated that. The and operator is true only if both of its arguments are true. So in the first row, P and Q are both true, and that means that P and Q is true. On the other hand, if either P or Q are false, then the and operator P and Q is also false. So we're going to have falses in this last column here. This is the definition of the and or conjunction operator. On the other hand, the disjunction operator, or, is true if either of its two inputs, P or Q, are true. So if both of them are true, that's great. But if just one of them is true, that's also enough to make the or operator true as well. And then if both of them are false, however, we are false here. So again, these are the definitions of these two operators. We'll see truth tables used to define other operators as well soon. Now let's try a more complicated truth table. This time, we're going to work with the logical expression not, and then I put in parentheses here, P and Q. So this means we're going to need to process both a negation symbol and a conjunction symbol. Much like in algebra, the right way to do this is to work inside out. So we're going to start with P and Q, and then we're going to apply the negation symbol to the output of that initial computation. So let's go ahead and get started. I've populated our truth values for P and Q, and then what we're going to do is we're going to have one new column for each step of the truth table that we need to compute. So I have one column for P and Q, and then another column for not P and Q. To fill in the column for P and Q, this is now where I need to start memorizing or otherwise sort of understanding what the and symbol does. I remember from the last video that the and symbol is true when both P and Q are true, but it is false otherwise. So I'm going to have 1 T and 3 Fs. And then I'm going to remember, okay, I'm going to apply the negation symbol, but I'm going to apply the negation symbol not to either P or Q, but to the column corresponding to P and Q, and that's the column I just did. So if I look at that column, well, the first entry here is that T, and so I'm going to negate that. I get an F. Then my next three entries are Fs, and so I choose T, 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 and that's the end of this truth table. I have computed not P and Q. When I'm doing complex truth tables, it's very important to have a column for each individual step, because otherwise you will make mistakes. I promise you, you will make mistakes if you don't take this step by step. So have a column for each stage of your computation in order to get to the result. Let's try another example that's complicated in a different way. So in this example, I am going to compute the truth table for P and Q or R. So Q or R is in parentheses here. That means I should compute that first. And then I need to compute the result of taking the conjunction P and with the result of Q or R. Because there are three variables, three logical statements that are involved here, my truth table needs to get taller. So in general, if I have k inputs, then I need to have 2 raised to the power k rows of my truth table. In this case, k equals 3, and 2 raised to the third power equals 8. And so I have 8 rows, one for each possible combination of the truth values of p, q, and r. So now let's go ahead and start our computation. So the first thing to not get confused by is when I compute Q or R, P is not involved in that. And so I am going to ignore the P column. I'm just going to look at Q or R. Q or R is true if there are any trues between Q or R. So true, true gives me a true, true, false gives me a true. Here's another one. In this row, both Q and R are false. That means I'm going to have a false. Here's another true, here's another true, here's another true, and here's a false. Now, when I do P and, now I need to look a little bit across the truth table. I need to look at this column, the P column, and I need to look at the Q or R column. And I'm going to ignore the individual Q column and the individual R column now. So P and, well, if P is true and Q or R is true, the conjunction is going to be true, and I'm going to have that in the first few rows here. But then if Q or R is false, then the conjunction cannot be true. I'm going to have a false here, even though P is true. Similarly here, when P is false, I cannot ever have P and Q or R be true. And so that completes my truth table. Again, here, when I have more inputs, more logical propositions that are ingredients to my compound logical proposition, I need to have more rows of my truth table. And when I have a sequence of logical operators like and or, both involved here, I need to have multiple columns in order to show my steps.